Welcome back to another video. To test variability, we use the chi-squared test of a single variance. The test may be left dash, right dash, or two-tailed, and its hypotheses are always expressed in terms of the variance, or standard deviation. A test of a single variance assumes that the underlying distribution is normal. As you can see in the bottom right figure, the degree of freedom of a chi-squared distribution significantly impacts its shape. So, it is important for use to identify the degree of freedom of a chi-squared statistic in order to retrieve rejection region or p-value for our analysis. Here, we are hypothesizing on the population variance. As a result, we are using a chi-squared test for all these three cases. To find the value of the chi-squared test, we need to plug in the values of sample variance, s squared, and the hypothesized variance, sigma squared 0. In case a two-tailed test, we are testing for deviations in both directions from the hypothesized value. To calculate the p-value for this test, we first find the value of the chi-squared test statistic, and then we calculate the probability of observing a chi-squared test statistic as extreme as the one we found, in either direction. Please note that as chi-squared distribution is not symmetric, we are looking into both tails for the extreme cases. If the p-value is very small, we reject the null hypothesis. The rejection region for a two-tailed test consists of both the upper tail and the lower tail of the chi-squared distribution with n minus 1 degrees of freedom. This is the highlighted area in part A bottom figure. If the test statistic falls within either of these regions, we reject the null hypothesis. These areas are determined by the chosen significance level. The upper-tailed test, case B, is used when we are specifically testing whether the population variance is greater than the hypothesized value as stated in the alternative hypotheses. In this test, the p-value is calculated by finding the probability of observing a chi-squared test statistic greater than the one we calculated. If this p-value is small, it leads us to reject the null hypothesis in favor of the alternative. In this test, the rejection region is in the upper tail, meaning we only consider whether the chi-squared test statistic is significantly large. If the test statistic falls within this upper rejection region, we reject the null hypothesis in favor of the alternative. The size of this rejection region is determined by the significance level, such as 5%. The lower-tailed test, case C, is used when we are specifically testing whether the population variance is smaller than the hypothesized value as stated in the alternative hypothesis. In this case, the p-value is calculated by finding the probability of observing a chi-squared test statistic smaller than the one we calculated. A small p-value leads to a rejection of the null hypothesis. In this test, the rejection region is in the lower tail, meaning we only consider whether the chi-squared test statistic is significantly small. If the test statistic falls within this lower rejection region, we reject the null hypothesis in favor of the alternative. Again, the size of the rejection region is determined by the chosen significance level. To use Python for hypothesis testing on the population variance using a single sample, we need to load the chi-squared test function and pass the necessary arguments. Here, we have a sample of size 30 of height of Italian men. We want to know if we can claim that the variance height of men in Italy is greater than 10 centimeters at 0.01. So, we need to run a one-sided hypothesis. Once the function is loaded, we need to pass the sample data, the hypothesized variance, alpha, and the alternative hypothesis, which here is greater. The function will return to us the corresponding chi-squared test, p-value, the rejection region, and a two-sided confidence interval by default. Here you can see the corresponding type 2 error for the two-tailed, upper-tailed, lower-tailed tests. Thank you for watching this video.
See you in the next one.